In today's video, we're going to explore the relationship between another pair of measurable variables that can be used to describe gases. Today's topic is pressure and temperature. To design this experiment, we start by picking which are our independent and dependent variables, and then we have to think about control. Probably the easiest thing to vary on purpose is the temperature, and so we'll use that as our independent variable, and pressure will be our dependent variable. We'll see if the pressure changes when we change the temperature, and if so, how does it do that? In order for us to have a good experiment that measures pressure and temperature effects, we have to control for two other quantities that may have an effect on the pressure. One of them is volume. That will not be too hard to control for by just using a container that doesn't change its size or shape. And we've already determined in a previous video that the number of particles does have an effect on the pressure, so we'll want to make sure that we control for that by having a sealed container. So this is the equipment that we'll use. We'll use a gas pressure sensor to measure the pressure of our gas, which will just be air. It'll be contained in a glass flask. The reason we'll use a glass flask is because its volume cannot change. The glass flask will be fitted with a rubber stopper that has two holes in it. One of the holes will just be plugged up with a valve that's closed, and the other hole will have a tube coming out of it that will attach to our gas pressure sensor so that we can measure the pressure as we change the temperature of the gas inside without the volume changing. Once we seal up both ends of that hose that connects the pressure sensor to the flask, we will no longer have any increase or decrease in particles, and so that will remain constant as well. We'll measure the temperature using a temperature probe, and that temperature probe will be inserted into a water bath, and the water bath will be on a hot plate. So we're not going to directly warm the air, we're going to warm up a bath of water that the air will be immersed in, and then we'll measure the temperature of the water bath. If we heat it up slowly enough, we should have the same temperature, or approximately the same temperature, of air as we do the water outside the air. This is what that would look like in practice. The flask is inside the water. We have to keep the air under the water as much as we can, and we swirl it around to make sure that the temperature stays even and doesn't get warm at the bottom and then stay cooler at the top, so that our temperature probe is measuring a good average temperature, which should be pretty close to the temperature of the air inside the flask. When I did this for 1800 seconds, so about a little over half an hour, I found that the linear correlation value is 0.9984, which is pretty good, and I don't see any pattern other than just some kind of randomness that seems to account for the fact that the correlation is not perfect. So I think a line is probably a decent model for this relationship between pressure and temperature. The slope probably depends a lot on the size of the container that I used and the number of particles that were trapped in it. The vertical intercept, well, let's think about temperature and pressure and see if it's reasonable that we should be able to throw out the vertical intercept. Remember, temperature is how fast particles are moving. So if our particle model is right, then the faster these particles move, the harder they should hit and the more often they should hit the surfaces of the container and also the pressure sensor. So it seems like as the particles slow down and get colder and colder, when they reach zero, they wouldn't be moving, and so therefore they couldn't exert any pressure because they couldn't collide anymore. So it's reasonable to think that we should be able to throw out the vertical intercept. Statistically, can we? If we look at the largest value of pressure that we record here, it's about 830. 10% of that would be 83. Half of that would be about 41.5. But our vertical intercept is much higher than 5% of our highest pressure value, and so it's not reasonable to throw it out. Why? Well, the explanation has to do with the fact that temperatures can be below zero in Celsius temperature scale. So when we reach 0 Celsius, that does not mean that no particles are moving. That's a sort of an arbitrary location on our temperature scale that has to do with the freezing point of water. If we extend this line and just keep going farther and farther and farther until we find our horizontal intercept, that would be the place where the particles aren't moving anymore, when the temperature actually has reached its lowest possible value and the particles are no longer moving. What we find from our data is that that's at negative 271.4. Scientists who have done this experiment and done it in other ways with other experiments have found that a more precise value is negative 273.15 Celsius. That's the coldest temperature that you can have. It's called absolute zero. Now, because it would be nice to be able to get rid of that vertical intercept and have just a direct proportionality like we do for pressure and number of particles, scientists invented another temperature scale. This temperature scale has the same size of a degree as the Celsius degree, but it starts at a different place. Instead of starting at the freezing point of water being zero, this actually starts at zero, at the coldest temperature there could be, negative 273.15. So here's our conclusion. If we get rid of that vertical intercept by using Kelvin temperatures only, then pressure is directly proportional to the temperature. And just like before, the most useful form of this comes when we divide both sides by temperature. So we see that the ratio of pressure to temperature is a constant, as long as we're using absolute temperature, in other words, the Kelvin temperature scale. So whatever happens to the temperature, the same thing must happen to the pressure. Double the temperature, pressure has to double. Cut the temperature in half, pressure also has to be cut in half. Now, how do we convert from Celsius, which is what we normally use, to kelvins? Because absolute zero is negative 273.15, you would just take your Celsius temperature and add 273.15. Now, for our purposes, that 0.15, we can just drop it and add 273 to any Celsius temperature. That will give us our Kelvin temperature. So what we learned from this experiment is that as long as we're using Kelvin temperatures, we have a simple direct proportionality between pressure and temperature. In other words, whatever happens to pressure, the same effect must have happened to temperature, and vice versa.